Hello, and welcome to Unapplied Maths, the YouTube channel where we practice maths without a license and hope to not get caught. Today, as part of the Talking Maths in Public Animation Challenge, I'm going to be sharing with you a curve of pursuit, or rather 6 different models for curves of pursuit that I've made in Geogebra. In the second part of the video, I'll be explaining how these models were created. So let's set the scene. In my model, I've got a blue lion who is going to be chasing a red penguin. Now, like all penguins, I'm going to let this penguin run around a little bit, and we'll see what the penguin does. The penguin runs in a circle. So what happens if the lion is going to try and catch the penguin? Well, there is a vector u that is connecting the line to the penguin, and the lion is always going to be running in that direction. But as the lion runs, it's going to be changing direction. So it's going to create quite interesting pattern. Now here, I've got a force vector, which is not really force, but I'm using it to think about as force. In my force vector of 0.1, this means that at every step, every iteration, the line is going to get 10% of the way closer towards the penguin. So have a think about what shape the line is going to draw out when I let him loose. On your marks, get set, run. Whoa, he goes off to a good start and then starts chasing the penguin. And we appear to be asymptoting towards a circle, a slightly smaller concentric circle. Is the line ever going to reach the penguin? No, because at every step, the line moves 10% of the journey and the penguin moves as well. Hey, look at that. It's Zeno's paradox. But you might be thinking that didn't really feel like a very fair journey. I can hit reset, by the way, and it will put the line back to the start. It doesn't feel like a very fair race and not very realistic. Because every time I restart the lion, he's moving very, very fast to begin with and then slows down. And I don't think a lion would actually ever slow down. And that's a fair point to make. So let's pause the lion. Let's put him back somewhere up the top here. We'll get rid of the trace. And we're going to move into model 2. In model 2, rather than letting the line move a 10% step towards the penguin, at each stage, I'm going to take the unit vector of u, so just find the direction and let the line move one step in that direction, hopefully keeping the line at a constant pace. And that might make a more interesting pattern when I let the line loose. On your marks, get set, go! Here we see a much smoother curve as the line gets towards the penguin. And then something a little bit interesting happens here because the line occasionally overtakes the penguin and has to come back to catch the penguin again, and it gets a little bit joddery and jerky. So let's pause the line. Let's put him back to where he should start. We'll start him off there. And here you might be thinking, well, I don't really trust that penguin, really. Why is the penguin just going in a circle? So I'm going to play with another slider that I've created here. And this is going to let the penguin move in a slightly wonky circle. So giving the penguin a bit of a chance to shake off the line by having a bit of a sharp bend. And we might see that jerky motion of the line a bit more pronounced here when I let the line loose. So what's going to happen this time? We catch the penguin up. The penguin moves at a different speed, you'll notice, as he goes around that hairpin bend. And the line is struggling to catch up. I can make this even more accentuated by finding one of my favorite shapes, which we see all the time in nature. And this is a lemniscate. That is a sort of ribbony shape. In fact, it's the infinity symbol. This is Bernoulli's lemniscate, if you're interested. So what happens if the lion tries to catch the penguin under Bernoulli's lemniscate? Let's have a look. He runs down, and he goes past, and then we get this really joddery pattern as the lion can't keep up. So clearly this model doesn't work too well. It's not very realistic. So let's move on to model 3. This time, in model 3, rather than the line only ever moving towards the penguin and trying to catch up by moving the same velocity at every step, we're going to model the lion and the penguin a bit more realistically. Lions are massive. They're much bigger than penguins. The penguin can swim around infinitely on this infinity symbol. But if the lion overtakes the penguin, he can't just stop. He can't turn a hairpin bend. So he's actually going to carry on moving. He has momentum. So this time, I'm measuring the vector connecting the lion and the penguin as a force vector. And I've introduced a new vector, W, which you can just about see here. And W is going to demonstrate the current velocity vector of the line. So to begin with, the line is stationary. The velocity vector is 0. At every time step, we're going to be adding a percentage of the force onto that velocity to change the velocity and then update the line based on that velocity, and we'll see what happens. Whoa, whoa, he's going all over the place. This line is actually trying to catch the penguin on the ice, and there is not very much friction on the ice, so the line is going all over the place. He's always trying to get close to the penguin, and actually this one is going a little bit mad. I think we can safely say this has now diverged, as the line is basically in orbit around the penguin being quite happy running around on the ice. So that's got a bit silly. Let's pause the line. Let's reset the line. I'm going to bring him back here, back to the start. When I click the reset button, the velocity vector W resets and the line comes back to 1. So imagine they're over here. I can hit reset. They both snap back to the beginning. Now, clearly, this one didn't work too well. And I think I can reduce the force even more. And maybe we just gave the line too much power, given that he's on the ice. So let's reduce the force and have another go. But this time, the line isn't going to try quite so hard, and see what happens this time. Oh, that's a little bit more manageable. We get this lovely kind of pattern emerging. The line is clearly always trying to get to the penguin, but it looks as though we're going to get back into this unstable orbit territory. And to be honest, I could watch this forever. This has a real vibe to me from 1990s screensavers. I find this really pleasing to watch. And one of the reasons why I haven't got around to doing this month's video up until the 16th is because I've just been enjoying watching these things go around and around and around. You could ask yourself the question, is the line ever going to catch the penguin in this particular model? And I don't really know the answer. I don't even think it's possible to calculate that. I think that's going to take too much computational power, and it's clearly not a stable orbit. Is it unfair that we're letting the penguin run around in an infinity symbol? Well, how about I put the penguin back onto that circular path instead? Oh, and he just missed him. It's something definitely has changed. Here, the force appears to be getting more unstable, which I do find quite interesting. I think that's because the penguin is got a different resonance frequency, and so we hit this idea of an increasing resonance and it getting divergent again. I'm gonna stop this though, because I think this is still fairly unrealistic. So let's keep the penguin going in a circle, just because it's quite nice to start with a circle and then go back to the lemniscate. And what about if we tried to make this a more realistic simulation? In the last example, the line was running around on ice and he constantly had force coming towards the penguin. But what about if we take this chase back onto the savannah, back onto the lion's territory? Because then we have an idea of friction, that the line can cling onto the earth and slow down a little bit. In fact, what if we do my favorite thing to do whenever I'm on safari in the savannah and fill the savannah with treacle, so that the line isn't just slowing down with some friction, but also has to constantly push against an idea of drag. So as we move into our fourth model, I'm now introducing this idea of a drag force. At every step in this system, I'm going to increase drag actually. At every step in this system, we're going to be reducing the force component by just 1%. To try and take out some of that divergent energy. The energy was getting too great. Let's see if we can reduce that a little bit. Starting with a circle, wait till the penguin goes, and off you go, lion. What's going to happen this time? So it's only been a 1% reduction. I haven't touched the force. What are we expecting to see? Is it going to go off the screen? Is it going to converge? Will the line catch the penguin? I don't know. It appears as though we have something a lot more stable. The line is now inside the penguin circle. Has the line converged to its own concentric circle like we had before? It's hard to tell. It's hard to tell. What about if I pause the line, reset it, and go back to the lemniscate? Let's put the penguin back in this infinity symbol. Will it still have, I'm not going to touch the drag, not going to touch the force. Will it still converge when we've got this slightly less stable rhythm? Let's have a look. So off you go, line. See if you can catch that penguin. Something's happening. What is going on with the energy? Is the energy increasing? Is the energy decreasing? It's hard to tell. It definitely looks like it's decreasing, but I don't know. The line and the penguin definitely go past each other a lot. I didn't actually put in anything to test whether the line has ever caught the penguin, but it feels as though we've hit another resonant frequency where the force vector W is largely going between the left and right, not really going much up and down. I think we've hit some kind of resonance. So let's pause the line. Let's reset the line. Let's increase the force to something a little bit higher, and then also increase the drag as well. See what effect that's going to have on my system. So let's release the time again. Oh my goodness, here we go. So this line is now very, very highly powered. It's like a spring, but also a hefty amount of drag. So it's not going too far away either. It's a bit more lively, a bit more playful, a bit more fun. And you can see that the line is tracing out a sort of bow tie shape that more closely conforms to what the penguin was doing, which is very interesting. I should point out, as I record this video, it's the first time I've ever used these particular numbers. I've rehearsed this a couple of times. I've played with it quite a lot, but I haven't used these specific values. I'm choosing them somewhat at random. So my narration is observing something for the first time, just as you are seeing it. But I'm pretty confident to say that the line has converged to a interesting shape. I'm not going to comment further on what that shape might be, but it's still fairly unrealistic. And if you think for a moment about what makes this system unrealistic, I think it becomes obvious. The trouble is, I'm on a savanna full of treacle, and that's not really where lions and penguins chase each other. They don't live on a savanna full of treacle. They live in space. So how about if I move on to my fifth model, and I've taken away the drag because, as we all know, there's no drag in space. But in this situation, I'm going to let the force change depending on the location. In the previous example, the line had a constant force that was applied in different directions, and then there was some drag component going on as well. But the power of the line was stable. This time, I'm going to let the lion and penguin orbit each other a bit more realistically by saying the strength of the attraction is stronger when they are closer, less when they are further apart. And in fact, I'm going to go with the inverse square proportionality to follow Newton's laws. So let's see what happens then when I release the penguin in space to release the line in space to catch the penguin. On your marks, get set, off you go. Oh, what just happened there? He went right round. Okay, so clearly something awful has happened. My line is shot off into the deepest, darkest space. Let's bring him back with that reset button, and we'll see if we can tweak the numbers slightly. Clearly, the line had too much force. So let's reduce that force component right back down to something really, really tiny, and we'll have another play. On your marks, get set, off you go. Oh, that's a little bit better. And is he going to come back? Have we lost him? Is he going forever? This is interesting. I genuinely don't know if he's ever going to come back. It looks like it might be a really wide, oh, here it goes, a really wide elliptical orbit, perhaps, but then he's shot past again. Oh, and he's gone through. Oh, this is like a dance, isn't it? But he's definitely going off out into space. It's going to be hard to tell if we will ever reach a point where his gravitational attraction will converge to the mean he will always return back to zero and then come back towards the center, or will his gravitational attraction diverge to the point where he will never be able to overcome it again and always shoot off to infinity? That's an interesting question to ask about whether it is possible to start stationary and end up never returning to the center. And I'll leave that for you to figure out for yourself. But I'll let it do a couple more slingshots around so we can enjoy this. It appears to be doing some kind of threefold knot by the look of it, sort of a Celtic knot style, and that is just delightful. I'll let the line have one more attempt at this, but sliding S back to zero to put the penguin in a circle. Circles are, of course, much more realistic for how things actually orbit because they are more closely related to an ellipse. And we'll set the line off now, see what happens. He's gone around and he's slowing down. It does take a long time to slow down before coming back. And there he goes. And oh, he appeared to get faster that time. And is he going to come back? I don't know. This is exciting. Interestingly, the W force vector is still currently pointing away, which means he is still actually getting further away from the circle. But W is edging closer and closer towards A, which means he's exiting the circle at a slower and slower pace. If W ever reaches A, then that means he will be at constant velocity because the force vector has decreased. But you'd expect W to eventually push past A because W is always going to be acting in the direction of the vector from the line to the penguin, which is now pretty much parallel lines because he's gone so far out into deep space. So I guess the question is going to be which of these two factors is going to overcome? Is W ever going to be able to slow the line down enough to make him stationary and then eventually come back? And again, I don't know the answer to that, but it's an interesting question. Okay, let's pause the line. I'll let the penguin keep going in orbit because I like the penguin moving. He keeps me happy. I'll bring the line straight back to the start. And I think I'm going to go back to the lemniscate. Actually, should we do something a little bit in between? Something with a small cusp and then going around. I'll show you the lemniscate formula in a little bit. Here we go. So for my sixth model on curves of pursuits, when n is equal to 6, I'm bringing back drag. And I think, in fact, I want drag to be quite high because you might have noticed that lions are very light. They don't have much mass. Penguins definitely don't have much mass. The whole gravitational idea, that was a bit silly. Gravity is not how lions chase penguins. It's bungee cords. In my sixth model of a curve of pursuit, I'm going to imagine that this vector u connecting the line to the penguin is in fact a bungee cord and see how that's going to affect the lion-penguin relationship. We'll go back to the savannah full of treacle. So there is an element of drag. The line is going to be slowing down, but the force is always elastic. And for us, we're going to be taking the force of an elastic spring to be proportional to the amount of extension of that spring. And actually, to make things easy for the calculations, I've just said that force is equal to the length of the spring rather than the extension. So shoot me. But we're going to be playing around with this variable force in a different way. So in the previous example, in the orbital example, the force was decreasing as length increased. This time force is going to increase as length increases. So it's a bit of a flippity-flop reversal of situations. And for the sake of argument, my bungee cord cannot snap. It's never going to break. So it's something interesting is going to happen. Have a think. Is it going to immediately shoot off to infinity? Is it going to converge? You've got 2 seconds to figure it out. 1, 2, off you go, chase. Oh, and he goes past. Oh, is that increasing in energy or decreasing in energy? What do we think is happening? You can almost see the effects of the treacle. I think that energy is increasing. Oh, my vector snapped. Do you know what? I didn't think that could happen, but I've now lost the vector u, which means my line has gone out of range of Geogebra and we can't find it. So let's bring the line back and we'll increase the drag, bring it down to maybe a 5% reduction of energy each time, of force each time. See what happens this time. Is that going to be enough? Set the line loose. I should be able to tweak this to the point where it becomes interesting, not mathematically clear, but pretty. And sometimes pretty is more important. Oh, I've lost the line again. Okay, so let's decrease the drag right down to maybe 10%. We'll reset the line. Off he goes. What's happening this time? Maybe he's just got too much force. So let's decrease the force. I'll do this live rather than resetting him. So that's just reduced the force by a factor of 4. And that appears to have stopped the growth of the energy of the system, but it did have quite a lot of energy when I was doing that. So I'll hit reset. I'll get rid of the trace, hit reset, and just try it from a starting point here. And what's going to happen? Oh, yeah, this is definitely a lot slower. And it's making more easily visible lines. I find W a very interesting point to watch. In fact, I'm going to put the trace on W if I can catch it, because I think W itself is going to start doing something fun. And I'll tell you what this looks like to me. To me, this almost looks like the line is tracing out a square and W is tracing out a diamond. Is that what's happening? I think the asymmetry of the penguin is upsetting me. So let's go full lemniscate. We'll reset, we'll get rid of the trace, and we'll try it one more time. See what's going to happen now. W definitely has a curious pattern to it. and I can't describe what I'm looking at. So I'll revert to the classic teacher trope and just say, what do you notice and what do you wonder? Well, I think I can predict what you might wonder. I think you're going to wonder how all this has been made. So let's have a little look behind the curtain and see what's going on here. Some of the most interesting things for me are going to be the shape of the penguin's path. I'll leave that running whilst I do the description. The shape of the penguin's path. So for that, I have used a lemniscate, and I take it. Actually, I'm going to take the trace off W because that's distracting. I'll show you the equation for the lemniscate. It's this one here. And for this, I've basically taken two equations and superimposed them upon each other. So the lemniscate should be cos b over 1 plus sine squared b, and also cos b sine b over 1 plus sine squared b. But I've introduced another parameter s so that I can let s go between 0 and 1 and basically turn on or off different elements of the function. So you'll notice there's an s here and an s here. If s is 0, that turns off this sine squared part, meaning it's just divided by 1. And that makes the function simpler. So it takes away an integral part of the lemniscate. The other integral part being the cos b for the y value here. You'll notice it's all in parametrics. The cos b is to do with the y value. If I set s equal to 0, then that cos b section has been destroyed, and we're left just with cos b over 1 and sine b over 1, which is a circle. But if s is equal to 1, then that has reintroduced the sine squared parts in the denominator. So by using that slider s, we can do a gentle transition between two different functions. Oh, the line has completely diverged. Let's reduce its. Well, I can't reduce the force or the drag. I'll tell you what, I'm going to go back to a slightly more pleasing example and set it running again whilst I narrate. There we go. So that's the lemniscate and how we transition from one to the other. A couple of other things to point out here might be the force vectors itself. And to do this, we need to investigate t. And in fact, we need to go onto the settings for t and have a look at how t has been scripted. So for t, I've gone onto the scripting menu, and here I've started using some JavaScript. So in my JavaScript, I have explained what I want it to do at each point. The key parts being get coordinate, so I can find the location of a particular thing, and then set coordinate, so I can rewrite a particular value. So really, just for the line, I was constantly updating where I wanted it to be on my page under various conditions for my various n equals 1, 2, 3, 4, 5, and 6. You might notice by the formatting of this, I didn't write the JavaScript. I can't speak JavaScript, but ChatGPT really helped me out with that one. The important thing to notice here is I've got it on the on update section, which is why my time parameter just constantly cycles through endlessly. Every time it moves, it updates the code, and the line has moved as well. So that's how I've got this whole thing to move. The reset button is another interesting one. For this one, it simply sets the coordinates of W and D, again, on update. So every time I click reset, it just jumps back to the 2 points that I wanted W and D to start off at. And everything else, apart from that, isn't really to do with how it's been built. It's just to do with the maths generally. So I'm not going to explore the rest of it. You can imagine that for yourself. I will publish this so other people can have a play with this applet, because I think it's quite fun. But my challenge for you then is when you're next creating a GeoGebra file, see if you can play with the JavaScript and make it do something interesting that almost feels like coding. It's a good way to take the difficult part of coding, well, the difficult part for me of coding that is in, say, PyCharm or a different IDE that uses console, and turn it into something that is immediately visual that can be shown in something more familiar like GeoGebra. And that's it for me today. I'll see you next month for another Talking Maths in Public Animation Challenge. Thank you very much for watching. Bye-bye.